guys, welcome to the atomic bonding tutorial. In this tutorial, I'm going to use elephants as an analogy for the behavior of atoms. And I'm going to talk about this elephant and his position relative to the ground. You'll remember during our physics unit, we talked about the fact that a roller coaster has more potential energy the higher it is from the ground, and more kinetic energy the closer it is to the ground. So you can store up energy, potential energy, in an object by lifting it above the earth. So this elephant in the upper left-hand corner has very low potential energy, gravitational potential energy. Basically what I'm saying is he's very stable there on the ground. He can't fall because he's already on the ground, and it doesn't take much energy for the elephant to hold himself up in this position. In fact, it doesn't take any energy. Just to the right in the next picture, this elephant is standing. Now, this is still a pretty stable position because he has 4 feet on the ground, but he does have some stored up potential energy. If this elephant were to suddenly lose his footing and collapse to the ground, just fall over on his side, you'd get a loud bang out of that, right? And some dust would go up in the air on that dusty road. So he would release energy by coming down to the ground. He would get it come out in the form of kinetic energy, heat and sound and light maybe. Probably not light. I doubt he's going to give off an explosion from falling. But the point is that this elephant in the middle picture on the top has a little more energy and is a little less stable than the one that's laying on the ground. Now on the upper right hand picture, I've put the elephant on a ball, and this clearly is unstable, right? He's got all 4 feet on the ball, which is okay, that's not too bad, but he's not on the ground. So now if this elephant falls, you're going to get an even louder bang and bigger release of energy because he's storing energy up by being above the ground. Bottom left elephant storing up even more energy because he's only got 1 foot on that ball. He's further from the ground the majority of his body. And of course, the elephant in the right bottom hand corner is an impossible elephant. But if an elephant were in this position, you would know that's a pretty precarious, unstable elephant that will produce a huge bang when and if he crashes, and probably injure himself in the process. So these elephants are like different atoms on the periodic table. The most stable elements on the periodic table are the noble gases. The noble gases, are these guys down here. And they are stable not because they're lying on the ground like the elephant, but because they have full valence shells. A valence shell is shown in this dot diagram. They have complete shells of electrons. Helium is full with just 2 electrons because the inner shell is all he has, and that inner shell can only hold 2 electrons, so it's full. All the other noble gas elements are full with 8 because they have an inner shell that's already full with 2, and they opened up an outer shell that filled up, and then in some cases even more shells. So these noble gases are unreactive. They do not have any stored up energy that they need to release, so they don't bond with other atoms because they don't need to. They're complete as they are. Just like this elephant can't fall to the ground, he's already on the ground. Elements in the middle of the table have a tendency to be pretty stable, like the elephant that's standing on all 4 feet. So this could be non-metals like carbon or nitrogen, or metalloids like silicon. And some of the metals, too, are fairly stable. Aluminum is stable, boron is stable. And a lot of the transition elements are pretty stable. So this has to do with the fact that they have a middling number of valence electrons, meaning they don't have very few, and they're not close to being full. They got 3, 4, or 5 valence electrons, all of which are reasonably stable. Not totally stable because, like the elephant that's standing up, they can bond, they can react with other things. And what they do, in order to react with other things, is they fill in their shells by either stealing electrons from other atoms or sharing electrons with other atoms. So those are going to be our 2 choices for how atoms bond. They can either transfer electrons from one atom to another, or they can share electrons. And in both cases, they're trying to do the same thing. They're trying to complete the outer valence shell. That's what makes an atom stable, just like the elephant is trying to get flat on his back on the ground. here are some unstable elements. These are the group 2 elements. They're not as unstable as some other elements, but it's like an elephant balancing on a ball. You've got beryllium, magnesium, calcium, strontium, and barium. Magnesium is shown here. You can see how reactive magnesium is. He doesn't react unless you give him a push, though. It's kind of like the elephant on the ball, right? If I want this elephant to come unbalanced, I got to give him a little push. A tiny little push on that ball, though, and this elephant's coming down with a loud bang. And that's what we do with magnesium. We give it a tiny amount of heat energy, and it takes that heat energy and turns it into a wild explosion. Calcium also is very reactive. Just put it in some water, pure calcium, and it will immediately begin to bubble and fizz and react chemically, because it is also like an elephant that's standing on a ball. Give it a little push, just give it some kind of chemical that it can react with, and it'll immediately go for it. The group 17 elements are called the halogens, and the halogens are all poisonous, dangerous gases. And these are colored gases, which is kind of neat because most gases don't have color to them. So you can see I have chlorine, bromine, and iodine gas. There's no picture of fluorine gas there. And these gases are chemically reactive. That's what makes them poisonous. And the reason they're chemically reactive is they're pretty unstable. And they're unstable because they're missing just one electron. So it's like they're almost complete, and they have this desire to be really complete. Of course, they don't have brains and they don't think, but I'm making a metaphor. I'm personifying the atoms for you so you can kind of understand what's happening. So these guys are like an elephant that's standing with 3 legs in the air and 1 on a ball. They're pretty unstable, and they will chemically react first chance they get. And the most unstable elements on the table, and probably the most fun, which is why we don't have any of them in the classroom, are hydrogen, lithium, sodium, potassium, rubidium, and cesium. Cesium is actually radioactive, so we wouldn't bring that into the classroom anyway. But you can see they're all metals, and they're all very shiny. You can see that they're in some kind of liquid there that's mineral oil, because if you just expose them to air, they're so unstable, they blow up. This one has been put in a little bit of water. I'm not sure which one that is. It looks like it might be lithium because that's kind of a reddish color to the flame. You put a tiny chunk of lithium in water and it bursts into flame. Sometimes it'll do it just sitting in the air, like I said before. So it's like this elephant that's balanced on its trunk. It's a really unstable, high-energy atom, and the second it gets a chance to put itself back on the ground, it will. And it'll do that by bonding with other atoms. When you come to class, I'll go into details on how the bonding happens, but I just want to bring up an example from our copper and sulfur lab. In your copper and sulfur lab, we heated the elements copper and sulfur together, and they bond with each other. There's 2 ways that they can do that, and so you can get one of 2 compounds plus another one that involves oxygen. I'm just going to focus on these 2 compounds. So you can either get copper 2 sulfide or copper 1 sulfide. And there's a reason for that. It's because copper comes in 2 varieties. There's the copper that has this dot diagram and the copper that has this dot diagram. And that's because copper has valence electrons that sort of go back and forth between there being 1 in the outer shell and 2 in the outer shell. If you go back to our Bohr model of the atom, you can think of it as if the valence ring, the outer ring, was overlapping with the ring underneath it, so that sometimes there's a valence electron in the outer ring and sometimes there isn't. And so you can have these 2 different versions of copper, copper 1 and copper 2. When copper 1 reacts with sulfur, you need 2 of them in order to fill in the 2 missing electrons on sulfur. Sulfur becomes complete when copper 1 gives away an electron, and you need 2 of them to give away, each of them give away an electron. Copper 2 becomes more stable when it just gives away its 2 electrons to sulfur. Now you might be wondering, that's great for sulfur, Mrs. Stracuzzi, but what about the copper? Isn't the copper now totally unstable without any electrons? No. If you look at copper on the periodic table, you'll see that there's a complete shell underneath the valence shell. So when you get rid of the electrons in your valence shell, the shell disappears, and the electrons underneath become the valence shell. So we're going to talk about this kind of bond. This is called an ionic bond. Not that you need to know that right now. And you can see that whenever you have an element from groups 3 through 12, you don't know how many valence electrons those atoms have. On the back of the periodic table that I gave you is a list of some of the more common transition elements and their different possible versions of themselves that you have. So again, this is all very, very unfamiliar to you. So what you might be wondering, well, what's going to be on the quiz? What's going to be on the quiz is not anything from this slide, I promise you. Okay? What I want you to think about for the quiz is, why do atoms bond with each other? And the answer to that is to become more stable. They become more stable by filling their valence shells, and there's two ways they can do that. They can either transfer electrons from one atom to another, or share electrons between themselves. So those are the key ideas that you need for your quiz. Okay guys, I'll see you in class.